Hello, everybody. We're going to do an exam problem from fall 21, test 1, and I hope we're seeing it here. And it's a mechanism. These are all mechanisms. I didn't copy the section that said do mechanisms for these reactions. Chromic acid oxidation is definitely going to happen on our test. We're going to do all of these mechanisms today without any short forms, just to remind you, you don't have to use the short form. So all one color. We got our lone pair on our oxygen here. And we're protonating that oxygen. We're getting chromic acid. And it's got, whoa, it doesn't have O, it has OH. With a plus charge. An OH here, OH there. It's activated towards attack by the alcohol. The alcohol is the only thing changing. None of this part is changing in this first part of the mechanism, so we're going with R. The alcohol lone pair is going to attack the chromium. We activated the chromium and then we attacked it. That's going to lead to an R attached to an oxonium, and we have a chromium. Chromium has 3 OHs, 2 OHs, 3 OHs, and a double bond to O and a plus charge on an oxonium. And we generated a sulfate ion in this first step, HO3 SO minus. And we're deprotonating an oxonium, leading to this intermediate, which is the hydrate of a chromic ester. That's a reminder you need to dehydrate your hydrate so that you have a chromate ester. So to do dehydration, we always need an acid-base conjugate pair. And in this reaction, we're using sulfuric acid over and over again. The acid portion's job is to do the protonation of the O to make it a better leaving group. So that's all we're going to do in this first step. Protonate the O, whichever O you want. We got 3 of them. One of them's got to go as water. I'll just pick this one. And we're going along here. We've got our chromium. We got our oxonium ready to leave. I almost forgot my oxygen up here. Nope, I just didn't draw it right. My goodness. Chromium doesn't have, chromium has an O bonded to the R. I don't know what was going on there. Here we go. Chromium has a bond to O, bonded to the carbon that is bonded to R. And let's make sure our chromium is all cool. We just protonated this O, and I'm sorry I flipped its position, but it's this O. And we still have 2 OHs we have to drop. We're going to do dehydration now. This bottom oxygen is going to become a double bond. And we're going to have to make this go up to here. Chromate ester. And what you do is you take your base, which you just made, OSO3H negative, Don't forget the anion. Grab H, make pi, leaving group leaves. That's a dehydration, which is a form of elimination. And now we have our R and our O, and we can do it to the left here. We got a chromium that looks just like chromic acid at the top of the screen. The only difference between this chromic acid, which is an ester, and this chromic acid, which is an acid, is OH is now OC. And we showed how that happened. The only thing remaining now is to make this pi bond. Right there. There's no pi bond. And most importantly, there's an H here. That H is not in the product. That is a clue what you must do. And water is what takes this. Generally, I try to remember to give you these two clues. I forgot on this test date. I usually remind you, you need those other two things, and that usually jars the student's memory into remembering water must pick up that proton. Sigma becomes pi. This is another elimination. This one's an elimination that reduces chromium. A little different. Okay. So that's a nice mechanism. We've seen it 3 times already just this semester, chromic acid oxidation. It is guaranteed to be on your test. The next one is also guaranteed to be on the test because chapter 16, we make imines, which are right here, and enamines. Yes, they will both be on a question like this, where it's most likely going to be intramolecular. So I'm thinking we might come back and let's just do it here. We're going to do this piece, and we can fill in the last part where we don't need a mechanism. You're reducing pi bonds to H's on each side. New H here, and I know you don't see it, but there is a new H here, and a new H here, and a new H here. Wasn't very accurate drawing where that bond went. Maybe it'll let me move it. There we go. No, it won't let me move it. So maybe I'll try to move it too far. Whatever. New H's. One way to do that with a pi bond that's not too polar, H2 and PT. That doesn't work with carbonyls very well unless you have pressure around too. Or I'll put a star here, asterisk, or NaBH4 in step 1 and HCl. That would also do the same job. Reduction of imines and enamines. So now we're going to do the mechanism where we make imine from a primary amine and an enamine from a secondary. So let's get right to it. I'm really not too picky about which one you do first. So you pick one to do first. I can keep my old R group if I react the carbonyl on the left first. Hey, how convenient is that? Let's do that. We're not combining any steps here. And what I'm going to do is on this one, I'll use a garish looking yellow arrow and go to the bottom of the screen. So I'll say this is going down here. And we'll just pick it up down there. We got our R. I'm going to have to remember what it looks like later. But right now, I don't need to remember. So R. And we attacked the carbonyl and made an O- with a lone pair of nitrogen. We attacked, that's this new bond here. We attacked with a nitrogen. And this carbon has an O minus now. And the nitrogen had this group, which we're going to label R prime for now. So we're finished. The isopropyl group with methylamino on the second carbon. I'll try to remember that. So there's an R prime on the nitrogen too. Don't forget, that's nitrogen with 4 bonds. That's an ammonium. Laws of pKa say this molecule will not exist for more than a femtosecond. Acid-base behavior must be obeyed. And you just have to show me that you know this O minus is going to pick up a proton here, but it's not from this molecule because it can't reach it. And we show that by using the intermole word. So we do an arrow, red arrow, grab that H. The arrow that can't reach is where you put the word intermole. Just put it right on this arrow here, intermole. Okay, and that does your acid-base reaction. And we've got an amino alcohol, an aminol, on the same carbon, the amine on the same carbon as an alcohol. And we remember that amines have lone pairs, which are fairly pushy. They can push off bad leaving groups like hydroxide. One of the rare times where I wrote on the whiteboard in class, you may have remembered that. And there we go. We have the conjugate acid of an imine. Make it into an imine. The base you just made comes back, grabs the proton. Whoa. That is a bad looking reaction arrow. I'm trying to make it look better. Not bad, not bad at all. So we made an imine. I'm going to draw out the other nitrogen now. We have an R attached to carbon there. We have an imine. Goes to a C, goes to another C, and up to a C, and on this C, we have NHCH3, and we need to draw our other R group out as well, because this nitrogen is going to attack it. Remember, there's a carbonyl in the other R. So the other R goes, there's CH2, then carbonyl, then 1, 2, 3, 4. CH2, carbonyl, 1, 2, 3, 4. I can do it. I got the CH2 already. I got the carbonyl. I got the 1, 2, 3, 4 with a methyl there. Third from the end. Let me verify. Methyl third from the end. We got it. Nice. Okay, we're doing one step at a time, no shortcuts. Let's do it. Nitrogen does what nitrogen did before. Attacks the carbonyl. Pi breaks, becomes lone pair with an O minus. And I don't think we're going to be able to do much circling on this one. That's how we have good practice at drawing molecules. Doing mechanisms over and over and over. We have to draw the skeletons over and over and over. And an N, H, methyl, CC, CH2, N, double, plus. O minus has to grab H, but it can't reach. Sounds like a familiar story. It grabbed it from a second molecule. It's identical, otherwise known as the old intermolecular proton transfer. You can use intermole, it's fine. All right, it's time to boot off the nitrogen again. Time to do it. Try to draw a little neater here. I say boot off nitrogen. I should have said time to use the nitrogen to boot off hydroxide. It's okay, talk is cheap. We're going to show it with a picture, which is worth many more words. There we go. We have an N with a methyl. Most importantly, it has its lone pair back, goes to a C with a methyl, CH2. Time to hoof off hydroxide, just like we hoofed off hydroxide here. Then the hydroxide is going to come and grab an H, but there won't be an H on the nitrogen this time. Oh my, that changes everything. Not really. It's going to grab an H from a different spot, ladies and gentlemen. So we kick it off. And here it is. 1, 2, 3. 1, 2, 3, 4. And double N right here. Let's see. We got that one right. Ooh. Didn't draw it the same this time. That's gonna come back and bite me, maybe. Double bond to. See, I did lose that CH2 a long time ago. Nobody's complaining. Nobody said anything. Nobody caught me. Okay, I'm out of the woods. I'm inserting the CH2 I forgot on multiple occasions. And then CH2, C double N. So I actually had it drawn right down here. Now, if you look at the product or products, no, just one. We need the double bond there towards the other nitrogen. And the reason why the double bond is here and not the other direction is these double bonds can resonate with each other. Totally irrelevant in this question. You didn't need to know that. You just look at what I need and you get me that product. I need the double bond here towards the other nitrogen. That means it needs to be here. There can't be a double bond there because this carbon has 4 bonds, 4 sigma bonds, one of them to H, but that tells you which H to take. When you're done, there's a double bond here with only 1 bond to H. This has 2 bonds to H. I only showed 1 because it's a mechanism. And you're done. And this resonates into here. And all I'm going to do is say it makes product X. Shrink, shrink, shrink. Shrink. Can't shrink it more. We can't even get this on the same page. This is X. There we go. Underlined X. Oh, I underlined. Good. So coming back, our next video will be same exam, same question, but the next part, 3C. We're going to do no shortcuts again. And then at the end of the video, we're going to do the hemiacetal-acetal mechanism right here with shortcuts. Sound like a game plan? I'll see you in a second. I'll come right back. If I can. Here we are.